Okay, problem 7, 8, 9, 10, and 11 all involve the use of the displacement equation, average velocity times time, and the acceleration equation, change in velocity over time. Alright, I redid these questions, so this is a bit of a modification from the packet I initially had handed out. So, race car driver starts from rest, reach top speed of 65 meters per second in 3 seconds. So, car, rest, V initial equals 0. Shouldn't have drawn an arrow there. Reaches V final of 65 meters per second and T equals 3.0 seconds. Okay, so organizational chart 1, 2, 3, 4, 5. V initial, V final, V average, acceleration, displacement, and time. V initial is 0 meters per second, V final 65 meters per second. Time is 3.0 seconds. Alright, so first thing we do here is find the average velocity since we are given initial and final. So the average velocity is literally the average of 65 and 0. So 65 plus 0 divided by 2 is 32.5 meters per second. So how far the car moves, that's displacement. Alright, those are the two things we're looking for. So delta x equals average velocity times time. So that equals 32.5 meters per second times 3.0 seconds. You know, it doesn't go 65 the whole time. It would go a lot farther if it did. It has to get up to that speed. So 32.5 times 3 is about 98 meters. Alright, acceleration is change in velocity over time. So that's plus 65 meters per second. We're going from 0 up to 65, so we're gaining 65 meters per second in a time of 3.0 seconds. So 65 divided by 3 is about 22. Acceleration is about 22 meters per second each second. And there's our two answers. Spacecraft orbiting, so we got some spacecraft orbiting at a uniform speed of 1050 meters per second. Alright, firing of one of rockets gives an acceleration, so it's going to accelerate. I'm going to use a different style arrow to represent acceleration. It's firing its rocket, and now it's going 2000 meters per second. The acceleration was 50 meters per second each second. How much time will it take to get up to speed and the distance traveled? So, same organizational chart. The initial, V final, V average, acceleration, displacement, and time. The initial speed is the 1050 meters per second. V final is 2000 meters per second. Acceleration is 50 meters per second. We don't know delta x and t. So let's find V average. So the average velocity here is 1050 plus 2000 divided by 2. It's about 1525 meters per second. So the displacement, delta x, equals average velocity times time. That equals 1525 meters per second times, I don't know the time. So I know the acceleration change velocity, so let's go there. Acceleration equals delta V over t. So we're gaining how much velocity? Delta V is how much velocity we're gaining. So one way I can do that is I can do V final minus V initial over t. So V final minus V initial, it's 2000 minus 1050 over t. And it's 50 meters per second, right? So this would be 950 over t, and that's meters per second, multiply both sides by t, divide by 50, we get t equals 950 over 50, because it's going up by 950 meters per second by 50 meters per second each second. So 950 divided by 50 is 19 seconds. So once you get that, you can put that back in over here. The 19 seconds we solved goes in here. That's from that. Okay, we got it here first though. So 1525 times 9 is 13,725 meters. Probably could have just called that 14,000 and that would have been good enough. All right. Moving on. Pause this real quick. Rocket accelerates upwards from rest. Uniform acceleration of 4.2 meters per second for 8 seconds. Okay. Acceleration is upwards. It's acceleration plus 4.2 meters per second each second. The initial is 0 meters per second. All right, and the time of flight is 8.0 seconds. So organizational table. The initial, the final, the average, acceleration, displacement, and time. 0 meters per second is the initial. Acceleration is 4.2 meters per second each second. Delta x we don't know. T is 8.0 seconds. Want the final velocity of the rocket and how far the rocket travels. So I can't do how far the rocket travels until I know the final velocity so I can get the average velocity. So I'm going to start over here actually with acceleration equals change in velocity over time. Multiply both sides by t. Change in velocity equals acceleration times time. So the change in velocity is 4.2 meters per second each second times 8.0 seconds. So 4.2 times 8 is 34. So our velocity changes by 34 meters per second. So again, therefore, the final must equal 34 meters per second, because it changes by 34, right? And we started at 0. That makes the average velocity 17 meters per second. The average is 0 and 34. It's just half of 34. It's 17. So now I can use that, right? Delta x equals average velocity times time. So 17 meters per second on average times the time of 8 seconds. 17 times 8 is 136. And there's that. Brakes on a car traveling at 16 meters per second permit it to decelerate at a rate of negative 0.8 meters per second squared. Determine the time it will take the car to stop and the distance the car will travel while stopping. So it's already traveling 16 meters per second, and then it needs to stop. The initial equals that, the final equals 0, a equals negative 0.8 meters per second squared, so the acceleration is negative. It's actually going that way, it's slowing down. Alright. The initial, the final, the average, acceleration, displacement, and time. 16 meters per second. The final is going to be 0 meters per second. The average, therefore, is 8 meters per second. It's half of this, halfway in between these two. Acceleration is negative 0.8 meters per second squared. The negative sign, we'll talk about why we're doing that. So, how long is it going to take to stop? Well, I know the change in velocity is going to be negative 16. I know the acceleration, so I can use this formula. A equals delta V over t. Cross multiply the A and the t, so t equals delta V over A. Therefore, t would be negative 16 meters per second at a rate of negative 0.80 meters per second squared. You get the time to stop of 16 divided by 0.8 is 20. 20 seconds to stop. That's good. Then displacement equals average velocity times time. So delta x equals 8 meters per second. That's the average speed it's moving at. Times the time, 20 seconds. 8 times 2 is 16. 20 times 8 is delta x is 160 meters. Very cool. An airplane accelerates constantly and reaches liftoff speed of 96 meters per second over a distance of 300 meters. So we've got an airplane. That's a terrible airplane. Alright, start some rest. V initial equals 0. V final equals 96 meters per second. Does it over a distance of 300 meters. V initial, V final, V average, acceleration, displacement, and time. V initial is 0 meters per second. V final is positive 96 meters per second, which makes 48 the average. Alright, it does it over a distance of 300 meters. Time it takes to get there. Well, for this one we can start off with delta x equals average velocity times time. Right? We're looking for time though. So divide by time, divide by V average, divide by V average. You get t equals 300 meters at a rate of plus 48 meters per second on average. Right, 300 divided by divided by 48. It's only going to take this plane about 6.3 seconds to get up to speed. So the acceleration is positive 96 meters per second in a time of 6.3 seconds. So 96 divided by 6.3. Oops, syntax error. 96 divided by 6.3 is about 15. Acceleration equals plus 15 meters per second or so. Well, I guess I was a little off the page here, but there's that, number 11. Number 12, I have another video where I go through and keep solving for time and plugging it into another equation. Use variables and see if we can couple new equations to use. So we're using these three equations really. We're using delta x equals average velocity times time. We're using acceleration equals change in velocity over time, which is v final minus v initial over t. And then the other one we're using is v average equals v initial plus v final over 2. Well, one of the things we're doing is plugging this into this. So we're going equation 1, 2, and 3. Let's go 3 into 1 and see what that gives us. So one thing we're doing is we're saying delta x equals v initial plus v final over 2 times t. Alright. One thing we do with this equation is we often say, alright, we can rewrite this equation as v final equals v initial plus a t. Alright, call that equation 4. If we take this vf here, we plug it in here. So let's do 4, let's call this equation 5 basically. Let's do 4 into 5. We get delta x equals v initial plus v initial plus AT over 2 times T. All right. Now we multiply the T through, so we get delta X equals, and add together the V initials, 2V initial plus 2V initial T plus AT times T over 2, which we'll rewrite as, we'll split this up, 2VIT over 2, we get VIT plus 1/2 of A times T, which is T squared. And that's the formula we saw before, right? That is delta X equals 1/2 AT squared plus V initial T. And that we've seen before. That was from the lab, that's been around.
Negative pass.
The next thing we're doing here is I'm doing one more thing. I got to this phase in this equation, and then we could have taken that equation, solved the acceleration formula for time, and plugged in it. So you get delta X equals V initial plus V final over 2, and then we go solve this equation for time, right? So it's times V final minus V initial over A. All right, and you get this wacky thing. You get delta X equals, and you get a FOIL this top here. You get V initial, V final, minus V initial squared plus V final squared minus V initial, V final over 2A. Well, that cancels, that cancels. Bring 2A upstairs. You get 2A delta X equals V final squared minus V initial squared. Bring the V final, you get V final squared equals V initial squared plus 2A delta X. Now I have another video where I go through this quite a bit slower. And these two equations are super important. We call this one L Grande and the timeless. And we can use those on later problems, which I'll make a video later on for.